Many software engineers struggle to understand the time complexity of an algorithm, and that's because they haven't found yet this video where I explain how it works in simple terms. First, the definition. Time complexity is simply a function which describes how the execution time or the runtime of an algorithm depends on the input size. For example, if we take a look on this function, we can see that it takes an array of integers of size n and it just overrides the first element with the value 10. Because this algorithm doesn't depend on the input size, so no matter how big the array is, it just only cares about the first element, it means that the complexity is constant and we express that through big of 1. Now instead, if we have a for loop where we override each element in the array with the value 10, the time complexity becomes big of n because now the algorithm depends on the array size. Moreover, if we override each element with the same value n times, then the complexity becomes n squared. Now in practice, there are a couple of well-known time complexities and it's really important to understand how they compare between them. We got linear complexity, so big O of n, which means that the execution time grows linearly with the input size. We also got log n time complexity, where the execution time grows way slower as the input increases compared to the linear complexity scenario. Algorithms with those complexities are usually the fastest ones. There's also n log n complexity, which is commonly known for sorting algorithms, and also we have quadratic complexity, usually found when computing two-dimensional arrays. So if we sort those complexities from fastest to slowest, left to right, this is the actual order. Now I'm sure you got the idea around linear complexities, so let's double click on the logarithmic ones because those are sometimes a bit tricky to really understand where they come from. So we're going to explore next binary search and quicksort, and we're going to start with the first one. Binary search is an algorithm which takes a sorted array and a number and tells us if that number is present in the array or not. It does that by checking the element in the middle of the array, comparing it with the number that we search for, and then looking in the subarray which has non-zero chances to contain our number. In this case, 11 is smaller than 66, so it will never be in the right side because the array is sorted, so binary search will look on the left subarray. The process continues on this one by checking the middle element, comparing it with our number, and then it gets found on the first position. So binary search took 3 steps, or 3 iterations if you want, to find our number. Now let's count the number of steps binary search takes relative to the input size, which is n. In the first step, the array where we search the number has n elements. In the second step, we discard half of the array, so then the search area becomes n divided by 2, and then n divided by 4, and so on. And if we tag the last step with k, we're going to have n divided by 2 at the power of k equals to 1, because in the last step, we remain with only one element. So basically, we have n equals to 2 at the power of k, and if we apply a logarithm with base 2, we're going to have k equals log n. So binary search takes log n steps to compute a result. And this is the time complexity of this algorithm, which is the fastest one, by the way. Now another algorithm which has logarithmic complexity is QuickSort, which, as the name says, it does in-place sorting of an array. The way it works is pretty clever. At each step, it selects an element in the array called the pivot, and it reorganizes the array such that all the numbers smaller than the pivot are positioned before the pivot, and all the numbers bigger than it will be placed after this element. This operation is called partitioning, and it's executed by swapping elements until this rule holds. After the array is partitioned, the same process applies on the 2 subarrays from the left and the right side of the pivot. And this process continues until the entire array is sorted. Now, because after each partitioning we split the array in 2 subarrays, it means that we have log n steps, the explanation being similar to the one in the binary search case. And of course, we need to account for the time complexity of the partitioning process, which takes n steps when the array is full, and it decreases with each split. Now the time complexity of the entire algorithm is the number of levels, or the number of splits, multiplied by the time taken on each level. So we got log n levels, and we're going to take the dominant factor for the partitioning process, which is n. So this gives us big of n log n time complexity for QuickSort. Now let's see what happens when the array is already sorted. We're going to always take the first element as the pivot, and because all the other elements are bigger than it, we're going to have only right subarrays, which means that the partitioning process becomes suboptimal. So instead of log n steps, we're going to have n steps, which means that the complexity is n squared in the worst case for QuickSort. Now here are 2 tips and tricks that you should know when computing time complexity of an algorithm. First, you need to identify and express the time complexity relative to the dominant factor of the function. In this case, we have 2 sequential for loops, which both have linear complexities. Even though technically we can express the complexity as big of 2n, we're going to drop the constant and keep the dominant factor, which is n. This rule applies with all complexity types, as you can see in those examples. And secondly, it's very important to visualize what the algorithm does when evaluating time complexity. If we take this case, we can see that we have a function which makes 2 recursive calls. It's not straightforward to compute the time complexity of this algorithm, but if we visualize the tree of calls, it looks like that. Each call makes 2 other calls with the value decreased by 1. So the total number of calls is equal to the sum of powers of 2, which is 2 at the power of n plus 1 minus 1. So the dominant factor is 2 at the power of n, which gives us the time complexity of this algorithm. So with that, thank you for watching, and I'll see you in the next one.